Hello everyone, I'm Akanksha Jain. I'm going to present the paper A ConvNet for the 2020s by Suwang Liu. So let's get started. This paper takes a spin on modernizing traditional convolutional neural networks to make them a stronger competitor against advanced vision architectures. The roadmap is as follows. Two model sizes in terms of flops are considered. ResNet 50 Swin T regime flops approximately 4.5 into 10 to the power 9. ResNet 200 Swin B regime flops approximately 1.5 into 10 to the power 9. Network settings. Applying similar training techniques used for training VIT, macro design, ResNext, inverted bottleneck, large kernel size, layer-wise micro designs. Training techniques are as follows. Number of training epochs is equal to 300, optimizer is equal to Adam W. Data augmentation consists of mix-up, cut mix, rand augment, random erasing. Regularization scheme consists of stochastic depth and label smoothing. Macro designs. First, changing stage compute ratio. The authors decided to change the state compute ratio of ResNet 50 from 3 is to 4 is to 6 is to 3 to 3 is to 9 is to 3 is to 3 is to 9 is to 3. This change resulted in an improvement of 0.6% on the ImageNet and the classification task as compared to the baseline, and the model's accuracy moved from 78.8% to 79.4%. Second is changing stem to patchify. The stem cell is the first layer of neural network that processes input images. So authors decided to change the stem cell of ResNet 50 by convolutional layer of size 4 into 4 with a stride of 4 to get non-overlapping patches with a receptive field of equivalent size. This change resulted in an improvement of 0.1% as compared to previous stages result, and the model's accuracy moved from 79.4 to 79.5%. ResNextify. ResNext has a better flops than a normal ResNet, and the core component is grouped convolution. It increases the network width to the same number of channels as that of Swinty's, that is from 64 to 96. As a result, it got an improvement of 1.2% in the model's performance, and as it went up from 79.5 to 80.5%. Inverted bottleneck. The multi-layer perceptron block in SwinT was compared to the ResNet block in ResNet 50. It was observed that the MLP block of SwinTiny, the hidden dimension is 4 times the input layer, whereas in ResNet, the 1 into 1 convolutional layers project down the input feature to apply 3D con and then project it up. As a result, the feature's dimensions was made similar to the MLP block of SwinTiny. An improvement of 1.1% by introducing this change into the network was observed, and the model's performance improved a bit, that is from 80.5 to 80.6. Large kernel size. The size of convolutional kernel of ResNet 50 is 3 into 3, whereas the size of local attention of MSA blocks of Swin transformer is 7 into 7. Experiments with different kernel sizes, that is 3, 5, 7, 9, 11, were carried out, and performance increased from 79.9 to 80.6, but flops were roughly the same. Micro designs. Some minor modifications were done to the network to get final convex block. Those changes are called micro changes, and they are listed as under. First is replacing ReLU with GeLU, then use of fewer activation functions, then use of fewer normalization layers, substituting batch norm with layer norm, separating down sampling layers. The results are as follows. Isotropic convex versus VIT. Convex can perform generally on par with VIT, showing that convex design is competitive when applied in non-hierarchical models. The result is shown below. Results: object detection and segmentation on COCO and semantic segmentation on ADE20K. The first table consists of the results of object detection and segmentation on MS COCO. The second table consists of the results of semantic segmentation on ADE20K. Conclusion: the widely belief is that the vision transformers are more accurate, scalable, and efficient than ConvNets. The authors introduced another architecture named ConNext, a pure ConvNet model which can favorably compete with state of art hierarchical vision transformers on various computer vision benchmarks while retaining the simplicity and efficiency of simple ConvNet. The authors hope that the new results in this study will challenge several widely held views and prompt people to rethink the importance of convolution in computer vision. Thank you.